Have you ever looked up at the night sky and wondered what the universe is really made of? We see stars, galaxies, but there's this huge invisible puzzle piece, dark matter.
hmm
It's something like, what, 26% of the observable universe's mass energy? But we can't see it, we can't touch it, just, yeah, one of the biggest cosmic mysteries out there.
It really is baffling, isn't it?
Yeah.
It's like having this giant slice of your cosmic pie, totally invisible, yet we know it's there. You can see its gravity pulling things around.
And today, our deep dive is getting into a leading candidate for this elusive stuff, a hypothetical particle called the axion.
Right.
We're going to explore, why scientists think it might exist, how they're hunting for it, and here's the really cool part. How the European Space Agency's Gaia mission,
Gaia.
which was meant to map billions of stars in our galaxy, is actually kind of unexpectedly revolutionizing the search.
It's a fantastic example of how science works sometimes. You get these insights from, well, seemingly unrelated places. It's cutting-edge physics, astronomy.
So our mission today is basically to give you a shortcut to understanding one of the biggest puzzles in cosmology. You'll walk away knowing more about this hunt for the invisible.
Exactly.
Okay, so let's start with the basics. We often hear cold dark matter. What exactly does cold mean there?
Right. So the main model for the universe is called the lambda CDM model. The CDM bit stands for cold dark matter.
Okay.
And cold just means these hypothetical dark matter particles were moving really slowly back in the early universe. Very sluggish.
Sluggish.
Yeah, think of them like cosmic snails almost. Because they weren't zipping around, their free streaming length, basically how far they could wander before expansion slowed them down, was tiny.
Ah.
And that allowed the very first structures, the seeds of galaxies, to start clumping together almost right away. It's at the minimum scale for everything that formed later.
So slow movement meant easier clumping. Got it. But how do we even know this invisible stuff is really there? What's the actual evidence?
Oh, the evidence has been piling up for a long time, nearly a century actually. Started way back in 1937. Fritz Zwicky was looking at the Coma galaxy cluster.
Vicky, yeah.
He calculated its mass based on how fast the galaxies were moving and found way more mass than you could account for just by looking at the stars and gas. Something unseen was there.
And that wasn't just a one-off.
No, not at all. Much later, in the 1970s, Vera Rubin and Kent Ford and also Ken Freeman, they studied galaxy rotation curves.
Ah, the famous rotation curve.
Exactly. They saw galaxies spinning so fast, especially stars way out on the edges. Well, if it was just the visible matter, they should have just flown apart. Something massive, invisible was holding them together, like a gravitational glue.
I remember hearing about that. It's just wild that stars on the outskirts move as fast as those near the center. Totally defies normal gravity with just visible stuff. What about more recent evidence?
More recently, we've got really compelling evidence from things like gravitational lensing.
Where light bends around massive objects.
Precisely. We see light from distant galaxies getting distorted as it passes massive, unseen clumps of matter. And then there's the cosmic microwave background.
The Big Bang's afterglow.
Right. The tiny temperature variations, the patterns in that light, match perfectly with what you'd expect if dark matter was around in the early universe. Plus, these huge computer simulations like Illustris,
Yeah.
they the large-scale structures we see today, if you include cold dark matter. They strongly back up the whole picture.
That's a lot of different lines of evidence pointing the same way. But is everyone on board? Are there any other ideas, like serious alternatives?
Well, there are alternatives being explored, like modified Newtonian dynamics, or MOND. But honestly, the overwhelming consensus in cosmology right now is that cold dark matter, whatever it is, exists. Its nature is the big mystery. So for this deep dive, we're running with that consensus. And to figure out what it could be, we need a quick detour into the standard model of particle physics. Because candidates like the axion, they live outside that model.
Right, the standard model. Our best inventory of fundamental particles and forces. Well, 3 of the 4 forces anyway. Gravity's still the odd one out.
That's the one. It gives us the quarks that make protons and neutrons, the leptons like electrons and neutrinos. Those are the matter particles, the fermions.
And then the force carriers?
Yep, the bosons. Photons for electromagnetism, gluons for the strong force, the W and Z for the weak force, and, of course, the famous Higgs boson found in 2012.
Giving mass to everything through the Higgs field.
Exactly. That's our current bedrock understanding.
But dark matter, as you said, it pushes us beyond that. So where do things like WIMPs fit in?
WIMPs, weakly interacting massive particles. They're a whole class of hypothetical particles, not in the standard model.
Weakly interacting, meaning hard to find.
Extremely hard. The idea is they mainly interact through gravity and maybe the weak nuclear force.
Yeah.
Very rarely bump into normal matter, but they could have been produced like crazy in the very hot, dense early universe. So they're a prime suspect for cold dark matter.
Okay, so if they barely interact, how on earth do you look for them?
It's tough. Scientists are trying a few angles. One is indirect detection, looking for signals like gamma rays or neutrinos
Hmm.
that might be produced if WIMPs bump into each other and annihilate, maybe in the center of our galaxy where dark matter should be dense.
Hmm.
Then there's direct detection, building ultrasensitive detectors, usually deep underground to shield from other noise, hoping to catch that incredibly rare ping of a WIMP hitting an atom in the detector.
Like finding a needle in a haystack.
Or maybe a needle in a few thousand haystacks, yeah.
Mhm.
And particle colliders like the LHC, they try to actually create WIMPs by smashing particles together at huge energies.
Yeah.
See if they pop out.
So WIMPs are definitely a major focus, but you mentioned another candidate, the axion, and it came from solving a totally different problem.
Exactly. The axion wasn't invented to be dark matter. It was proposed to solve something called the strong CP problem in particle physics.
The strong CP problem sounds intense. What is that?
It's a bit technical, but basically the theory of the strong nuclear force quantum chromodynamics, or QCD.
The force holding quarks together.
Right. Mathematically, QCD allows for a term, a part of the equations, that should make the strong force behave differently for matter versus antimatter. It should violate what's called CP symmetry charge conjugation and parity.
Meaning it should treat particles and their mirror image antiparticles differently.
Parity, yeah. And if that term was there, it should have led to a huge imbalance between matter and antimatter right after the Big Bang. But when we look around, the universe is overwhelmingly matter. We don't see big CP violation in the strong force. So why is that term zero? Or incredibly close to zero? That's the puzzle.
Okay, a mismatch between the theory and what we see. So how does the axion fix it?
Well, in 1977, Roberto Pacheco and Helen Quinn proposed a new symmetry. And shortly after, theorists realized this implied a new particle, the axion. It's predicted to be incredibly light, much lighter than an electron, and interact extremely weakly.
And its job is.
Its existence basically introduces a mechanism that dynamically cancels out that problematic CP violating term in QCD. It automatically adjusts to the strong force interactions to preserve CP symmetry. So it elegantly explains why the universe looks the way it does, with matter dominating.
Wow. So it solves this deep particle physics issue, and then people realize, hey, maybe this incredibly light, weakly interacting thing could also be the dark matter.
Precisely. That's the beautiful connection. It
That,
wasn't designed for dark matter, but it has just the right properties. Stable, very light, interacts very weakly, could have been produced in the early universe. A perfect candidate.
that is fascinating. Are there other candidates we should quickly touch on before we dive into the axion hunt?
Yeah, very briefly. People have considered macroscopic things, like Macho's massive compact halo objects, like faint stars or planets, or even primordial black holes formed right after the Big Bang. But they have their own issues and aren't the main focus for today.
Got it. So axions. We have this particle solving one problem, maybe being the dark matter. How do you actually find something like that? So light, so elusive.
Yeah, that's the challenge. The main experimental strategy for decades has relied on something called the Primakov effect.
Primakov effects.
It's the idea that an axion can convert into a photon, a particle of light, in the presence of a strong electromagnetic field. And vice versa, a photon can turn into an axion.
So you build a really strong magnet.
Exactly. You build a very strong magnetic field in a resonant cavity, basically a tuned metal box, and you just wait, hoping that ambient axions from our galaxy's dark matter halo drift through, hit the magnetic field, and poof, turn into a tiny flash of light, a microwave photon that you can detect.
Like tuning a radio to the right frequency, but for axions?
That's a great analogy. These experiments are called haloscopes because they're scanning the dark matter halo. There are quite a few famous ones, like ADMX, the Axion Dark Matter Experiment, plus others like Haystack, Kultask, Organ.
Are they finding anything?
Well, they're making incredible progress in sensitivity, ruling out certain axion masses and couplings. But so far, no definitive detection. There are also underground experiments like Deep 3600 in Canada, which are now using results from Gaia and other surveys about our galaxy's halo structure to better target their searches.
It's amazing the effort going in, but the fact that these direct searches haven't found anything yet, that's where Gaia starts to come in, right? The lack of direct detection makes people look at alternatives or other ways to constrain things.
That's exactly right. The null results have definitely spurred interest in maybe slightly different dark matter ideas like fuzzy dark matter or warm dark matter, which axions could potentially be part of. And yes, Gaia, the ESA star mapper, it's become this incredibly powerful, unexpected tool in the dark matter hunt.
Okay, this is the connection I'm really interested in. How does mapping stars help find tiny particles? It feels like totally different scales.
It does, but it's about the subtle, indirect effects these particles could have. Stellar evolution is a key area. Think about white dwarfs.
The remnants of stars like our sun.
Right, these super dense cores left behind. Their cooling over billions of years is mostly driven by emitting neutrinos. But if axions exist and can be produced inside stars, they would provide an extra way for the star to lose energy, making it cool down faster.
Ah, so it changes the cooling rate.
Exactly. And the luminosity function of white dwarfs, basically how many white dwarfs we see at different brightnesses, is very sensitive to this cooling rate. Gaia's incredibly precise measurements of white dwarf brightnesses and distances allow scientists to put really tight limits on any extra cooling from axions. They can say, okay, if axions existed with these properties, the white dwarf should look different than what Gaia sees.
So Gaia's data acts like a constraint. That's clever. Any other stellar examples?
Oh yeah, red giants are another one. Specifically, the very tip of the red giant branch in stellar evolution diagrams.
Okay.
The brightness of stars right at that tip is very well understood theoretically. But again, if axions were being produced in their cores, they'd carry away energy. This would mean the star's core has to get a bit more massive before helium fusion ignites, which subtly changes the brightness of that tip.
And Gaia can measure that brightness precisely enough.
Absolutely. Using Gaia's distance measurement to the Omega Centauri star cluster, for example, researchers set some of the world's best limits on how strongly axions could possibly interact with electrons. It really narrows down the possibilities for what the axion could be like.
That's incredible, using star clusters as particle physics labs. Now, I also saw something kind of wild, the boson star idea. How does Gaia feed into that?
Yeah, that one's definitely more speculative, but very intriguing. Gaia recently helped discover a system with a sun-like star orbiting what looks like a black hole, but the orbit is, well, a bit weird. It doesn't quite fit standard models of how such a binary system should form and evolve. Okay, so some researchers proposed an alternative. What if the dark companion isn't a normal black hole, but a boson star? A stable, dense clump made entirely of bosonic particles, potentially axions or something similar.
A star made of bosons.
It's a theoretical possibility. Gaia's precise measurements highlighted an anomaly, and that sparked this really creative, out there thinking about fundamental physics. It shows how good data can push boundaries.
So Gaia's not just looking at stars, it's using them and other cosmic phenomena as probes.
Exactly. Take low-frequency gravitational waves. These ripples in space-time could come from the very early universe. Inflation, cosmic strings, maybe phase transitions. And axions could leave an imprint on that background.
But aren't LIGO and Virgo looking for gravitational waves?
They are, but they're sensitive to higher frequencies.
Yeah.
Gaia, by tracking the tiny motions of billions of stars over years, is essentially a giant detector for very slow, low-frequency changes in space-time. People are actively analyzing Gaia data to search for signals that LIGO and Virgo can't see, potentially revealing clues about axions or other early universe physics.
And weak lensing, too. How does Gaia help there?
Weak gravitational lensing is the tiny distortion of background galaxy shapes caused by the gravity of foreground matter, including dark matter. Gaia's precise positions for countless stars provide an unprecedented reference map. This helps measure those tiny distortions much more accurately, letting us map dark matter on smaller scales and probe its properties.
It's amazing how this one mission keeps finding new applications. What about structures inside our own Milky Way?
Absolutely crucial. Gaia has been revolutionary in discovering stellar streams. These are like long, faint rivers of stars orbiting in our galaxy's halo.
Remnants of things the Milky Way ate.
Exactly, either shredded globular clusters or dwarf galaxies that got tidally disrupted. These streams are fantastic tracers of the galaxy's gravitational field, which is dominated by the dark matter halo. Studying their shapes, their density, how wiggly they are, that tells us about the halo's structure and even its lumpiness.
And how does that link back to axions, maybe the fuzzy kind?
Right. If dark matter is fuzzy, meaning it's made of extremely light bosons like axions that have a wave-like nature on galactic scales, then the halo wouldn't be perfectly smooth. It would have density fluctuations, a sort of quantum interference pattern. Simulations show that these fluctuations would gravitationally perturb stellar streams, potentially making them thicker or puffier than they would be in standard cold dark matter.
So you compare Gaia's stream data to simulations.
Yeah, you can set limits. For instance, some studies use stream thickness to put a lower limit on the mass of these fuzzy dark matter bosons. Other simulations use Gaia data to refine the standard halo model itself, which then feeds back into improving the targeted searches by experiments like ADMX or D183-600. It's a really productive cycle.
Gaia's data improving the direct searches. That's direct impact. What about those ultra-faint dwarf galaxies Gaia found? Crater 2, Antlia II.
Those are fascinating. They're incredibly dim, but seem to have enormous amounts of dark matter compared to their stars. They're so diffuse and dark matter dominated that they challenge both standard cold dark matter models and modified gravity theories. They're outliers.
And why are they particularly interesting for axions?
Well, some researchers argue that the properties of Antlia II, especially its large size, and the very slow motions of its stars, are hard to explain unless dark matter behaves like a Bose-Einstein condensate on galactic scales.
A quantum state where particles act like one big wave.
Kinda, yeah. This naturally happens if dark matter is made of ultralight bosons, like axions with a mass around 1022 electron volts, incredibly tiny. This specific mass happens to be what string theory sometimes predicts for axion-like particles. So Antlia II might be pointing towards this wave dark matter or fuzzy dark matter picture where the axion's quantum nature becomes important on galactic scales. Similar arguments have been made for Crater 2.
Okay, we're getting into some really cool, maybe more speculative territory now. Are there other ways Gaia might probe axions in the future?
There's some really neat ideas. One study looked at whether tiny periodic wobbles in the Gaia satellite's own motion as it orbits could be used. If there's a background field of something like dark photons, which are related to axions, it might cause minute periodic deflections in the apparent positions of stars. Gaia might inadvertently be acting as a probe for this unexplored parameter space.
Using the satellite itself as a detector, what about those weird triangular features seen in Gaia data?
Yeah, that's another intriguing one. Some researchers noticed peculiar triangular patterns in the distribution of stars in velocity space. They suggested these might be caused by stars passing through a caustic ring, a region of focused density in our galaxy's dark matter halo.
Okay.
And here's the really wild part. They proposed that the sharpness of these features could be explained if dust particles were being gravitationally dragged along by cold axion flows within the halo. It's a direct link between axions and visible galactic structure, if correct.
Cold axion flows. That paints quite a picture. And finally, this idea about galactic disks getting thicker.
Right. This ties back into the fuzzy dark matter idea. If axions are ultralight, around that 1022 eV mass, they behave like cold dark matter on very large scales, fitting cosmological observations. But on smaller galactic scales, their wave nature dominates. Their effective wavelength can be huge, like kiloparsecs across.
Bigger than star clusters.
Yeah. This inherent fuzziness might naturally solve some problems standard CDM has on small scales, like predicting too many small satellite galaxies. And one consequence could be that these fuzzy dark matter waves gently heat the stars in a galaxy's disk over time, causing the disk to gradually thicken.
And we see evidence for disk thickening.
We do. Older stars tend to have more spread out, hotter orbits. The amount of thickening observed in our own solar neighborhood seems to match quite well with what you'd expect from heating by fuzzy dark matter with that specific ultralight axion mass. It's another piece of circumstantial evidence pointing towards these kinds of particles.
Wow. Okay, so let's try and wrap this up. We started with this huge mystery dark matter. We looked at a top contender, the axion, born from particle physics and the challenging hunt for it. And then we saw how Gaia, this amazing star mapping mission, has just completely transformed the landscape. It's constraining axion properties through stellar evolution, probing them with gravitational waves and lensing, using galactic streams and dwarf galaxies as labs. It's bridging cosmology, astrophysics, particle physics.
It really underlines the interconnectedness of it all, doesn't it? How peering closely at stars, these tiny points of light, can tell us something fundamental about the invisible scaffolding of the entire universe. It's beautiful, really.
It absolutely is. And it really makes you, the listener, think, doesn't it? How could this tiny, almost undetectable particle, the axion, if it exists, be shaping everything from the way galaxies form down to the subtle dance of stars that Gaia is measuring? What other secrets about the hidden universe is Gaia just starting to uncover for us?